All right. Today, and maybe we'll go this far, hopefully go this far, maybe do a problem or two, and get the homework in your hands. If we got that far, I think I would be fine. And then we'll move on. We'll talk about some different things. The chapter's got a lot in it. It's got mechanisms. It's got it talks about enzyme reactions towards the end of the chapter. And so you can get into, after you kind of know the kinetics, then speculating on what's happening with the reaction. Let's just do a little bit of math review real quickly. We talked about this on Friday. The integrating dx over x is what?
Oh, it's ln of x. It's log base e if you want to be specific.
Well, let's just use ln.
Okay.
This is what's in the book.
Sometimes people get kind of mad with you.
The ln of, well, let's see, what's the other one I want to do? The integral of dx over x squared.
Oh,
Negative 1 over x.
Okay, so here with x squared, n equals negative 2, and this is negative. This is negative. No, this is n minus 1, or n plus 1 over 1 over x to the n plus 1. Is that right?
Yeah.
So if n equals negative 2, you have negative 2 plus 1 over 1 over x to the negative 2 plus 1. You got negative 1 over... It's not x to the negative 1. What am I doing wrong here?
That's negative 1 times 1 over x. That's right, isn't it? Well, if you have it, if it's negative 2.
Oh, it's times x to the n plus 1. Is that what it is?
Yeah.
That's it.
Yeah, but what you have right there is 1 over x to the negative 2. It's actually just x to the positive 2, right? Because it's still in the denominator.
This here?
Yeah. It should just be 1 over x squared plus 1.
Yeah, or this right here.
The original one, that first one. Because if you have 1 over x to the negative 2, it's actually just going to be x squared. So it's just it's just 1 over x squared plus 1. And the denominator.
I see what you got. I see what you have. Gotcha. All right, and then the ln of 2 over 4. I mean, we could solve that on our calculator, but that is the same as the ln of 2 minus the ln of 4. Or it's the same as minus the ln of 4 over 2. Right? Okay. So that's roughly the calculus that we'll be using. When the calculus goes beyond this, we'll probably just settle for the derived equation. And that's what we'll get into here. But for those things, for the first order, second order in one reactant, and zero order, we're fine with that calculus. All right, so here's where I want to begin. I want to begin with the first order, deriving the first order reaction, the integrated rate equation for a first order reaction. And I would put this under the heading for you guys, like what if on the exam there was a question, derive the first order, the integrated rate equation for first order reaction or second order. I don't know how far we'll go with that analogy, but think of it in those terms. We want to walk down through getting to this integrated rate equation and looking at it in different forms, etc. All right, so these reactions are first order in the reactant, first order overall. So simplest thing would be where you do have A producing B or A producing B plus C, whatever it is. In these cases, A equals B plus C. And here's two examples, N2O5 decomposing into N2O4 and oxygen, or uranium decaying into thorium and helium. These are first order reactions and first order overall. Okay, and this is kind of where we're going, but here is where we're starting with these two rate equations. So let's start right there. Here's the rate law. The rate law basically says that the rate is proportional to concentration. And you take the proportionality out of there with a constant, K, the rate constant for that reaction. And here's just a general one. The rate equals K times A to the nth power. Now we're going to look at the case now where N equals 1. Okay, and we also know that the rate, you would describe the rate of this reaction. Let's just look at the simple one. A goes to B. We're going to look at the rate as the negative, the change in the concentration of A with respect to time. All right? We've said you can also express rates in terms of the formation of the product. In that case, it would just be the positive. Positive, the change in the concentration of B with respect to time. But we have those two equations. So let's just work with that. Let me try to write this small enough so that we can see maybe most all of it when we're done. We got those two starting equations. We got minus the change in the concentration of A with respect to time equals K times the concentration of A. And now remember, now we're looking at it with N equals 1. It's first order reaction. Now we can get all the terms for A on one side of the equation and the T on the other side of the equation. As a matter of fact, as we do this, let's just carry the negative over there with it. So the D of A with divided by the concentration of A equals negative K dt. Then we can integrate this from the initial concentration to the final is going to be equal to K dt from the initial time to the final time. So we're going to integrate both sides of the equation. All right, and we just said that we just went over the math. Now this is the case where N is negative 1 here. N is negative 1 here, and it is the exception to that integral we did with dx over x squared, that works except when the power is -1. So here it's the log. So this is ln of A final divided by A initial, and this is going to be -k times T final minus T initial. Okay, we just said you can invert this and change the sign, which we want to do here. So let's change the sign here and make this ln A initial over A final equals -k T final minus T initial. And of course, we can multiply both sides by -1. And get this expression. Okay, now we can simplify this a little bit further by just doing this where this accommodates whatever time you want, some intermediate time and a final time, whatever. But we're going to look at it from the start of the reaction. So we're going to set Ti is 0, time 0. And that's going to change our AI. We can refer to that now as A naught. And our AF is going to be the concentration of A at some time T. All right, so Ti is 0. And we're going to set TF is just going to be time, some point in time. So we got initial time is 0, some point in time is just time, and so we're going to have the ln of A naught over A final, AT equals KT. All right, you with me? Any question?
So we're saying A initial and A naught are the same thing?
Yeah, so we're saying the initial concentration of A is the concentration of A at time 0.
Yeah.
When we start the reaction. That's all we're saying here.
Yeah, that's fine.
And then we're saying the final concentration of A is just the concentration at time T.
Why don't we just integrate from 0 to T then?
Yeah, we could do that.
Okay.
And we get that. And so there's your integrated first order rate equation. That's equation 2014. And so that's where we get to, simplifying this. And recognizing that we're going to start a reaction with a certain concentration of A. We kind of know where we're starting. So we know what that is. And what we're really interested in is what is going to be the concentration of A at some time after the start of that reaction. Okay, so there's not a whole lot of steps in there, but a couple, and we get to that equation. All right, and so there it is, equation 2014. That's the integrated rate equation for first order reactions. A naught is molarity, moles per liter, or molarity. Time can be seconds, minutes, hours, whatever the time is, and you get an appropriate L unit on your rate constant. I got a bunch of blank slides in here. Okay, here's one example of a first order reaction is the isomerization of hydrogen isocyanide to hydrogen cyanide. So here's just the isomerization. Here is K. What mass of HNC, this is our starting material, remains after 1.5 hours if a 1 gram sample of HNC was present at the beginning of the reaction? And we could work down through that or just look at this. So we've got, here's our initial concentration. Our final concentration equals constant times, okay, the rate constant was given in reciprocal seconds. So we're taking the 1.5 hours and we're converting it into seconds. And get to the final concentration is going to be 0.00419 grams. Okay, what was that? That was example 20.3.
Why? That's not concentration though, right? That's just, I would assume that you take the mass and then you do the density and figure out your concentration that way. I guess it doesn't have how large your solution is, but that's mass, that's not concentration.
Okay, we'll see in a second, Liz, that although the brackets are referring to molarity, molar concentrations, you can use other things like percents or grams or whatever you want to, as long as both, as long as they're in the same. Because look,
well, it's natural log of one over the other, so the answer is
right,
no matter what.
Right. There it is molarity over molarity here. That's basically canceling out. You can use any concentration term you want to use there, as long as they're both the same.
Oh, okay.
Okay?
Yep.
Sure.
We'll see in just a second when we look at half-lives of these first-order reactions that you can work off of percents. You don't have to work off of molarity. But good question, because we are using the brackets there to indicate molarity, and I pointed it out right here. But it's a little more versatile than that. You do have to pay attention to that, because if you get into second order and other order reactions, the units are a little tricky. Because sometimes you're taking the natural log of the reciprocal molarity or something like that, and it's hard to really say exactly what that is. Good question. Okay, now let's just take a look at this equation one more time. We've got the natural log of A naught over A t equals KT. All right, now there's two other ways of representing this equation that are useful. One, we could invert this again and get that the natural, invert this, get the A up here and the A naught down here, and is equal to negative KT. All right? And then you could take the analog, well, let's work right off of that equation for a second. So then we get that, so there's two ways to work with this equation now. You can have the natural log of the final concentration minus the natural log of the starting concentration equals negative kT. And you can get the natural log of A time equals, and if you add this to both sides of the equation, all right, so there's one other form of it. We're just moving it into another form. What happened there?
I think there's a touchscreen.
What?
This is?
Yeah, I think so.
Let's see if it...
You like touched it, and all of a sudden it just like went up.
I'll tell you what, if it is, I'm getting it patented.
Ooh.
Okay, no, okay.
Darn.
But what we have is y equals mx, let's see, do we?
Here.
We don't have y equals mx plus b right there, do we?
If you flip around the KT term and the LNA dot term, is it MX plus B?
Yeah. Yeah, I guess so. So y equals mx plus b. Okay, so that's useful for graphing. And another way to graph it or represent this equation would be to take the analog of both sides. So you'd have this over that equals e to the negative kt, or you'd have okay, so here are two other ways this reaction can be represented, or this rate equation can be represented. All coming off of the original integrated first order rate equation. Yeah, so there, here's the analog of it. So really the concentration of A at any time t is equal to the original concentration times e to the negative kt, and that's coming off in that fashion. And here is a y equals mx plus b. So here's your x, y, x plot. It's a linear plot. Your slope is negative. You got negative slope. So the concentration is diminishing with time in a linear fashion. So you get a nice y equals mx plus b plot of it. So those are useful ways of representing these. Okay, sticking with first order for a little bit more here. Looking at time, looking at in terms of time, solve the first order integrated rate equation for time. Time is 1 over the rate constant times the log, natural log of the initial over the final concentrations. And so you define the half-life as the time required for the initial concentration to diminish to 1/2 of what it was originally. Half-life. All right, and so let's see, how did we get? Oh, okay. There's our initial concentration. What's our final concentration? At this half-life, the final concentration is 1/2 of what it was originally. So it ends up being just the half-life is 1 over the rate constant times the ln of 2. And notice now in this half-life equation, there's no concentration in it. The actual concentration is come out of there. It's just half-life is this number divided by the rate constant. Okay, so just knowing the rate constant, you can calculate half-life for a first order reaction. And the nuclear decay is first order reactions, and then other first order reactions, you can get the half-life just once you know the rate constant for the reaction. Because really what you've got here is originally you got 100% of whatever you got 100%. At the half-life, you're 50% of what you started out at. It's just a factor of 2. So half-life is ln of 2 over k. 0.6931 divided by the divided by the rate constant. Here's an example. We talked about hydrogen peroxide on Friday. Hydrogen peroxide decomposing into water and oxygen. First order reaction. Half-life is 6 hours. So every 6 hours, the concentration is diminishing by half. 1 molar, half molar, 0.25, 0.125, 0.0625.
Does it actually decrease that much every 6 hours?
Well, I haven't done that experiment, but I'm assuming it would.
Dang.
I mean, this
that fast, like by the time you get it up, by the time it gets to the store, it's already being like nothing.
well, no, the bottle in the store. This is with something there that's driving the reaction,
Oh.
catalyst or something. And one thing we haven't said there is temperature. But no, it's not like decaying like uranium is. This would be in the presence of bacteria or something that's causing its decomposition. No, the bottle's fine. Bottle's fine. Otherwise, the bottles would be exploding, right? On the shelf about every 12 to 14 hours. Reaction 2A goes to B is first order in A with a rate constant. How long would it take for A to decrease from 0.88 molar to 0.14 molar? Okay, let's do that. How long would it take? Time is going to be equal to 1 over K times the ln of the initial over the final. Is that the equation we had? Yeah, right here. What do we get?
That's 65.65 seconds.
Yeah, we're dividing by 1 over seconds, so the units is seconds.
Is that what you got there?
Yeah, that's what I meant.
Yeah, and all we did was take this and we flipped this. Oh, no, we had this up here, didn't we? We didn't flip it. And we're just dividing by k to get that expression. Okay. Okay, for right now, that's first order. We'll probably go into a little bit more detail with first order later. But let's look at a second order reaction. Now it's second order in A, so we have A going to B, but it's second order in A. So the rate is k times A squared. The rate is also the decrease in the concentration of A with respect to time. So if we just do what we did on the first order reaction, get all the A terms on one side, get all the rate terms or all the concentration terms on one side, we end up with this. And if we integrate this, and so this is going to be, the integral of this is going to be the 1 over A
negative 1 over AT minus negative 1 over A naught, so it would be 1 over AT plus 1 over A naught.
Okay, yeah. That
Yes.
is going to, we're not going to have a negative in here yet, are we? Oh, we've got the negative here. And we're going to do the same thing here, get rid of our Ti as 0. Is that right? Now the signs are still messed up here. Why is that? I think that, yeah, so if we want to get rid of the negative here, we got to multiply this. We're going to have 1 over AT minus 1 over A naught equals KT. Yeah. Okay?
Yep.
Is that right? You with me? And so then we get to this expression. Yeah, and so either one of these is really the integrated, this is the integrated second order rate equation. All right, so you can see we're always isolating the final concentration on one side and coming up with an expression that has the rate constant, time, and the initial concentration on the other side of the equation. Because this is what we know. This is what we probably already determined by, like, the homework assignments you did, where you figured out what the rate constant is for this particular reaction, and you got the time. And now you can calculate a final concentration at any particular time. So that's your second order rate equation. And this kind of walks down through it. Example 20.4 in the book just looks at the units, just says, hey, how would these units work out? What are the units for the rate constant for a second order reaction that has this rate law? dA over dt equals K times A squared. The rate itself has units of molarity per second. This term contributes molarity squared over, here's molarity per second, and that's going to distill down to molarity per second as you go through the dimensional analysis. Okay, let's see. Let's look at this example, 20.5, and makes an interesting point. It can still talk about half-life, but it makes an interesting point about it. So, consider the following reaction: carbon disulfide plus oxygen forming carbon dioxide and sulfur dioxide. And this is second order. It's given that this is second order in carbon disulfide. How long will it take for the concentration of carbon disulfide to drop to half of the initial concentration? For the following initial concentrations: 0.05 moles per liter and 0.005 moles per liter. So here's one, we're going to compare it to another one that's 10 times more dilute. I don't know, I might have to give you assigned seats.
The bracket is just so good today.
Can't even read my right line anymore.
Okay, what we had was 1 over the final, sometime t, minus 1 over the initial equals kt, right? So that's how they're setting this up. The question is saying, what is going to be the time at which that is going to diminish by a factor of 2, be half of what it started out originally. So you're working all this out, just solving for t. Where's their answer? T equals 65,100 seconds. For the first example, 0.05 going to 0.025. Here's the second example, 0.005. It's diminishing to 0.0025. And the time there is 651,000 seconds. And then it asks us in here, comment on the answers. Now, if this were a first order reaction, it wouldn't matter what the concentration was to start with. It would still take the same amount of time to get to have it, right? Take the same amount of time to have it. But that's not what's happening here. It takes 10 times longer to have this one here. So this is second order reaction. We can talk about a half-life, but on a second order reaction, the half-life is not independent of concentration. That's the point of this example. Okay? So when we talk about half-life of nuclear decay, and that's a very common way of approaching that, that's because that's a first order reaction.
First order overall.
Yeah, first order overall. And it's first order in the beginning concentration of your radioactive species. And so it has a half-life that is the same, whether it's 16 hours or 1,000 years or whatever, like uranium. Uranium has a very high half-life. It doesn't matter how much uranium you start with, it's going to take 1,000 years to have half of it. But here, it does matter what you start with. How long it takes to get to have that concentration is a variable in calculating that number. So don't just think half-life applies to every kinetic reaction the same way. Okay, we talked a little bit Friday about zero-order reactions, and here's the example the book gives, and this helped me start getting a better feel for this. The metabolism of alcohol to acetaldehyde or ethanol in the body, zero-order kinetics. Zero order. Doesn't matter. Now think about this, and then I'm going to want to challenge the biochemists. So that's Taja and Ryan, right? Okay? So think about it. If we say that you drink some alcohol, and the rate at which the alcohol is going to convert to ethanol is not, it's not dependent on the alcohol concentration. It's a zero-order reaction. It's going to convert to ethanol at some particular rate. It's going to have a rate constant. It is going to convert, but it's going to be independent of the alcohol concentration. So what's going on there? What's going on there? What does it take for the body to convert alcohol into ethanol? What does it take?
Magic.
Magic.
It's probably an enzyme of some kind.
Oh, you're the engineer, Grant.
I've never taken a bio class, but everyone else so like enzyme's always the answer.
Enzyme's the answer. Okay, so you have alcohol. And it's going to ethanol here. All right, but it has to form a complex, some sort of complex with the alcohol plus an enzyme. All right? Is the enzyme going to be very high in concentration? It's going to be very low in concentration. But it is going to be the rate determining step. The alcohol has to come into the enzyme and be converted. Come into the enzyme and be converted. So the enzyme concentration is constant, but it's controlling the reaction. I think that's what's going on here. That's intuitively what I see going on in my mind. You can have, doesn't matter how much of this you have, it matters how much enzyme you have. So the rate of the reaction is dependent on the concentration of the enzyme. And so it's going to go at a certain rate depending upon how much of that enzyme your body has available to convert it. And all the other alcohols to just wait. All right? But it's just as soon as that enzyme is available, it's converting it. So it's going at a constant rate. So the rate is equal to K. K times, this to the 0 power. Now, don't get tricked up right here. All right? Here's your initial concentration. Here's your order of the reaction, okay? So there's 2 zeros going in there. You're thinking, oh, one is an exponent. Yeah, that's the order of the reaction. And the other one is the initial concentration. All right? So a zero order reaction distills down to simply this. The rate of change of this with respect to time is just dependent upon the rate constant. We won't, well, here's what it looks like. Here's what it looks like. Here's a plot of a zero order reaction. It doesn't diminish off asymptotically. At 1 half-life, you have half of the material is gone. At 2 half-lives, it's all gone. All right, on a zero order reaction, 2 half-lives of the reaction, it's gone. The reaction is finished. So here's one case where this plot, a y equals mx plus b plot, it actually does have a y-intercept and an x-intercept. It's not going asymptotically. That's zero order. All right. This is where we'll start on Wednesday. Second order. Overall in 2 reactants. So this is this situation here. We got A plus B going to something, and the rate law is A to the first power, B to the first power. It's first order in each of the 2 reactants, or each of 2 reactants, and it's second order overall. We'll get into that one on Wednesday. Let me give you this homework and give you a little bit of an explanation. And maybe on Wednesday we'll do a problem or 2. We'll see what applies. Let me give you this proviso on this homework. This is Dr. Crane's homework assignment. Dr. Crane got his PhD in kinetics.
So I'm guessing it's a little hard.
I think so.
We're done for.
And I was gonna try to, my intent was to try to start crunching down through these, and I did one or two of the problems. I didn't do all of them. If we find one or two of them that are really hard, we'll, in other words, if I can't get them, we'll probably drop them
So we know that on Wednesday?
This will be due when?
Monday.
Next Monday?
We do next
We'll
Monday.
get back on Wednesday.
So by Friday, I mean, if you guys have a pretty good consensus that number 7 looks impossible, we'll probably drop it, okay?
Okay.
But scratch through them, certainly try all of them, and there may be one or two that get dropped. All right?
Thank you.
Thank you.
You're welcome. Be sure to read at least as far as we got here, and read the second order overall, first order of each reactant for Wednesday. For Wednesday. Anybody know they're going to see Dominic before Wednesday?
I know I won't see them.
If he's gonna be in my class tonight, I will see him, but I'm not sure how long his golf tournament is gonna go. But we do have a class together.
The 6th maybe on Wednesday morning,
That
that
might
might
be
be
better.
the earliest, yeah.
Probably doesn't matter.
Does he have an open study review session Tuesdays?
Yeah, he'll be all right if he gets this Wednesday.